calculated from the density, and I mentioned here this is the total density, including the ionic density. So of course, delta function at the site of the atoms, and then there's the electric density. That is the electric field, and if you remember, then you take the derivative with respect to one of these Cartesian directions, and you get this expression. So this is another way to write them. Tensor, which I showed you before, and then you took the eigenvalues of this, and you get these parameters, coupling and anisotropy. And basically, what you need to do is insert the T operator density for the electrons. That's what one has to do. I'm not going to show you the formula because it's just straightforward. Using the calculation analytics field gradient is very fast. If you remember, you have to do the linear response in the case of chemical shielding. Here you just need to reconstruct the density, use this formula, and you get the matrix. So usually this takes a couple of seconds, even for bigger systems, whereas the calculation of the chemical shielding can take quite easily days even in trial computers. But then there are some extensions. One of them was mentioned already, the J-coupling. There has been these authors, they showed what is the formalism of GIPAW in the case of J-coupling. Now we just wait for someone to implement. But it has been also extended to simple tensors, so that's of course only a numerical thing. Then some new physics comes when you go to the methods. So the NMR code, this is not implemented, by the way. Most of these three are not implemented currently for the mass present in some other codes. I will show quickly some results also for the night shift, what it is. And then there's the electromagnetic resonance, so what we will talk later. And then there was this other way to calculate NMR properties. If you would use that, then you want to reconstruct the core, use the GIPAW method. So now we have a little bit of time. I will just go quickly through some applications to give you an impression what can be done, and what kind of systems have been done, and what can be calculated, a little bit of the accuracy, what you can expect. So starting from the original paper, I showed you where the formula was given for the first time for GIPAW, and they compared then the values for chemical shielding or chemical shift to all electron calculations. These kind of methods for magnetic fields or magnetic response, they are implemented already since a longer time in codes for calculating molecules, and the GIPAW method was needed generalized for the periodic systems. So here, you have several contributions. Here the third term, the diamagnetic correction term and permanent correction term, you don't need to care about these. So if you just add those up, and here's the core contribution, or contribution in the core electrons. So here's the total value. And you see that, okay, in some cases you have a value of 400, and the variation is for silicon. You have variation in even over 200. So if you have a small, here they take a constant already, but you have the difference of 0.2. So actually, it doesn't make much sense to keep so many digits. But this was also interesting in the beginning to see if you take the all electron values and values from GIPAW, you get usually very close. So they are within 1 ppm, so these are the ppm, so half a million. And I don't know where you get some divergence of a couple of ppm, but really the range can be 100, 200. So if you have a difference of 4, it's still very small. So the accuracy of GIPAW seems to be.
What are the typical experimental values?
I will show you for different systems later, but I mean the values experiments, they are of the same order.
What is the typical magnetic field used in such system? And what is the corresponding temperature? Is room temperature? All experiments are at room temperature? Low temperature?
I mean, these for molecules can do room temperature. And then most of the experiments, I think they had, I mean, for crystals, for example, they had room temperature.
And magnetic field?
It's, I think, a couple of Tesla, maybe 10.
10 or 20 Tesla, yeah.
So good, very strong magnetic field.
I mean, still we say that you can, it's a small perturbation. I think it's close to what you can do in engineering can do. Then I mentioned the second application, this is the paper where they showed the formulas for the electricity gradients for the first time. I'm using GIPAW. And well, just to note you, what was the, well, 2001 was the time, so the method is almost 10 years old now. And this came somewhat later, 2003. And so this is now a comparison of some of the values. This is the first chemical shift from experiments and from theory. These are different crystalline forms of silicon dioxide or silicon. And well, here you see that the range is 30. And then if you compare, of course, you would want to have exactly all the points in the diagonal. That would say that the theory values are exactly or perfectly accurate. They're not exactly there, but the difference is quite small. You have some, there's 4 or 5 ppm errors, but they are more in diagonal. So what you have is qualitatively, you have everything well in place. Silica is quite easy material in a sense, but I mean the remaining errors, is it exchange correlation functional, or is it some numerical things? That remains to be seen, but this is what you can expect really for the accuracy. Well, then for the electricity gradients, if you remember, there are 2 observables which I mentioned. One is the CQ coupling, and then this the anisotropy. Well, here you are almost in diagonal, you have some more variation. Here, well, I wouldn't really say that the points line, not the line, but there are also experimental errors. And the overall get quite a good accuracy. So, especially in the chemistry field, and molecules usually, they discuss a lot what is the effect of exchange correlation. They have different parameters. It's just to reproduce better the magnetic properties or the responses. But I would say that this is already very encouraging. I'm not even sure whether this is LDA or GGA. But you get this kind of quality usually.
So these are from dynamic experiment, because megahertz means frequency.
I mean, this is just a unit for the
Shift.
unit.
What is this eta?
This was the anisotropy. If you remember, the 2 eigenvalues, you have E6 minus VYY divided by V, etc. So it goes from 0 to 1. The range can be in theory.
Why the scatter is so, spread is so high in case of anisotropy?
Well, maybe it's more sensitive for small numbers because you now take the difference of the 2 eigenvalues. So it seems that it's one of the forms of the diamonds. I mean, more or less all the other crystalline forms, they are the line, but these diamonds, they are all. Maybe there's something else that experiment. Then, just to mention other kind of materials, for instance, silicate. And first they calculated some some values, so the isotopic, so the trace of the chemical shielding tensor. Sorry, this is the chemical shift tensor. So you take average of the tensor, and with these numbers, they have defined also the anisotropy of the chemical shielding. With this, one can go and simulate how it would look like. So this is again the same table. One can simulate how that would transform in the experimental spectrum. Solids, you don't get such simple peaks, like I showed you before, with the finite correlation times, but you get something which looks a bit more strange. So you get a very the line, which is not that smooth. That's the experiment. Using these parameters, one can simulate the spectra, and you get, I would say, very encouraging agreement. So also for this material, you get that.
What these two peak attributes to?
Sorry?
What these two peak attributes to?
Oh, I don't know. Go to. I mean, the shape of the is always characteristic. In the solid state, you get all these side peaks and these kind of shoulders. And I'm not an expert on interpreting the experiment. So what they get out of those experimenters, they get out the chemical shifts. It's like this. We can go the opposite way and model in the spectrum. Well, another application, this is for carbon nanotubes. And they calculate first susceptibility, so magnetic susceptibility alone, and the perpendicular to the tube. So if you know the carbon nanotubes, they're these one-dimensional objects kind of wrapped from graphene. And this is as a function of the diameter of the nanotube. So the bigger the nanotube, so you start to converge towards some value. And so this is just these two are how close the nanotubes are to each other. You know, it's very difficult to isolate the nanotube. So what they calculate was both isolated and then bundled and then interacting. Qualitatively have the same values. And so they, as a function of tube radius, they converge. And these two values they have from tight binding calculations for finite radius or graphene. So single layer ultra out the nanotubes, and the same here. So if you would go to very large values, you would probably approach the tight binding value. So in principle, one can use the tight binding to get the susceptibility of. And then for the chemical shift, one has to do the proving the electron structure explicitly. And this is now the chemical shift as a function of the radius. So it's difficult for the experimentalists to compare with these values, because if you know when you produce carbon nanotubes, you get nanotubes which, first of all, they have all different kind of radii, and second, you have some of them are metallic. These are only calculated for semiconductor nanotubes. So you have a full range of values what you would get. The experimental signal is very marginal. They would use these curves to interpret what is the radius, the chemical shift experiments. Then I mentioned the metals. I just quickly show some results. So first for two simple metals, and copper is also quite simple. So if you calculated the chemical shift and then to experiment. So if one is not that close, but within, let's say, 10-20%, one can reproduce the values. And then this is this is not a quantitative value, but this is the contribution of the different parts of band structure of this lithium for the night shift. The night shift is like a little bit like the chemical shift, but it's because you have metal, you put the magnetic field, so part of the electrons, they shifted or lifted from below permanently with different spin, and some of them become occupied. So it's kind of response, and of course it's very strong at permanence, because you need small magnetic field or small change to get a large change in the electronic structure close to permanence. Well, we have also quite a contribution. So these kind of things one can calculate in the whole. And then one could quantify this with the night shift. This pure number, but I didn't take any examples here. Then I will maybe quickly go through one more applications. I was myself participating in this, so I can tell you some more details if you want to know. But this is a calculation for a glass called Pt2 boron oxide, and there was an interesting physical problem behind that. There was a controversy in the literature. What is the fraction, which is called Kf, of so-called Boroxol rings? So these are boron atoms, these are oxygen atoms, and you have always, this is the unit, structural unit, and then here you have those triangles which share a corner. So that's a so-called Boroxol ring. And then one has molecular unit where the ring kind of doesn't close. And then the question was, or has been a long time in the literature, what is the fraction? I mean, does the glass compose of this kind of structural elements or of this kind? And the experiment said, okay, it's mostly Boroxol rings like this, and the molecular dynamic simulations, first for classical and also some ab initio, first principle molecular dynamics, said, okay, it's 0 to 30%. So what's the reason for this contradiction? And we think we found the solution. And if I just know auto list, so doing the straight molecular dynamics gave these F values of which were very small, but there was a person in Japan who came with a kind of biased way of doing molecular dynamics, and he gave us molecular dynamic samples which had a high fraction of these rings, like the experiment says. So if we do straight these simulations, we get this, but he kind of biased so that he got this sample. And when we did the first principle of molecular dynamics, we did the stability analysis, we saw that this is more stable. And that's the origin, in our respect, or in our opinion, of this controversy between these two. So in these molecular dynamic simulations, because if you remember the timescales are just well, the best case is nowadays you could go maybe to microseconds in classical simulations and milliseconds in ab initio or in nanoseconds in ab initio molecular dynamics. You cannot get the whole process how this glass is formed, because for those of you who know the timescales for making the glasses or the relaxation times, they are really long. They can be seconds and so on. So if you do a quick simulation of a couple of picoseconds using molecular dynamics, you don't necessarily get to the correct state of the matter. So we believe that this is true. We showed the stability as favoring this kind of fraction of the Boroxol ring than this, and then still to compare the experiments or to prove also the referees. Then we did some simulations of the observables, experimental observables, and so we have here two spectra. So the full line is the calculated spectrum, and the test line is the experiment from Raman experiments. And you see much more structure here because our samples are very small. But in principle, what you see that if we have a sample, the calculation with small fraction of Boroxol rings, we don't really reproduce this peak here. But when you have the high fraction, then you get very good agreement. This is a really good Raman spectrum fits much better with if you have the high fraction of peroxide rings. And then, since I'm talking about NMR, here's the simulation for NMR. On the left-hand side, first for the boron and then for the oxygen nuclei, the NMR signal, and here's the chemical shift. And now we have glass, we have distribution of chemical shifts, and you have some characteristic peaks. And if you look, for example, here, this is the calculated spectrum with the small fraction of peroxide rings. It doesn't correspond very well to experiments, whereas it corresponds much better, not perfect, but still much better, both peroxide and oxygen. It corresponds much better with the high fraction of peroxide. So by calculating this observables, or experimental observables from electron structure theory, we can convince ourselves that our model with high fraction of peroxide rings matches much better the structure than the small fraction. And the explanation was, yes, the simulation started from a low concentration of peroxide rings because the time scale is too short. They don't go to the correct ground state of the vitreous or the classic phase of peroxide. We started from the correct phase. We showed that it's more stable than the one that what is otherwise obtained from molecular dynamics. So then quickly about the implementation of the GIPAW module in quantum espresso. So there are other codes which include GIPAW. The origin was implemented by Hans Kamali and Chris Picard in the so-called Partey code. It's also incorporated in the Casted code, which is a commercial one, and then you have a quantum espresso. And then Jonathan Yates and me, we have a web page which is called GIPAW.net. There's not much yet, but at least there are some key references of the GIPAW method and the codes. For the GIPAW module in the codes, it can do NMR, so the chemical shielding and the electric field gradients, and it can do PPR, like David will tell you after the break, and it can, or the part of the GIPAW module of files are also used for the X-ray analysis. So there are two modules, and they one needs also to reconstruct the electrons close to the core for the nuclei, and that's what they use, the same technology for that part of the GIPAW module. Well, there are some limitations, like I mentioned, the vulnerability or ultra-tunable lenses are not yet implemented, and then there's a technical detail. If you do crystals which are not cubic or not orthorhombic, then the symmetry operations that you use, because you use them to reduce the number of K-points, they have to map coordinate axes to each other. And that's because of the derivation we had the magnetic field and observable along the XYZ axis. They have to map each other, otherwise the symmetry operations should be excluded. This unfortunately you have to do by hand. Well, then the pseudopotentials, I'll try to go quickly. You had already a session, I believe it was on Saturday, pseudopotentials, and these pseudopotentials are very similar to those ones, or at least those ones which you need for PAW. So you need some extra parts. So if you have, this is the input for the atomic code, so you have the part which generates you pseudopotential, so this is the non-conserving case, and we generate here the Julia-Martins pseudopotential for oxygen. So this gives you the pseudopotential. But for the GIPAW reconstruction, if you remember, you have a sum over the projectors. So usually we use two projectors for L value, for the angular momentum. And that's the reason why we had to add some projectors, or actually the all pseudo wave functions that we use to construct the projectors for the GIPAW. So what we did was we could do a small change in the input of the atomic code. So in the test section, one gives which projectors one needs for the reconstruction, so for the GIPAW part. So in this case, you have only 2S for the pseudopotential for the Hamiltonian. For the reconstruction, one has 2 S projectors, and one has 2 D projectors. Well, we don't reconstruct the D because usually the contribution is very, very small. There are then some details here. So the core radius we don't use, but this is then the reference energy where one has the second projector, and it has to be different than the eigenvalue what is the default for the first project. So one has to choose second energy. Here with 3S we take the default, which is the eigenvalue, and this is unbound state, so we take just the value here at 0, minus 0.1 Rydberg. One could also use scattering state. And just to mention that there are some numerical problems if you choose the 2 eigenvalues too close, and in any case one has to be careful when that creates this PA or this second projector for the reconstruction. So here I show you the eigenstate dashed line, the black one. You don't hardly see it, but this is the 2 p orbital Fock-String. And then we take another orbital, which is 3p, but I think it's just 3p in a sense that it's lying higher in energy. And we take 3 different values for the reference energy for that, and that gives you, well, this is again scattering state. But I think this was half a Rydberg, so several electron volts above the vacuum level. And then, well, depending which value you take, you get different wave functions. Do you think, okay, they look very different, that's a good basis for the projectors? Actually, the GIPAW reconstruction is done only inside the core radius. Here the core radius 1.4, and then we use still a scaling function which smoothens the wave functions so that all the wave functions at the core radius go to 0. And this is the result after smoothing. So the dashed line is the 2p wave function, and then the 3 different ones. And one chooses usually one. So one has the eigenstate plus another one. Which one to choose? You see that after the scaling and so on, they look all pretty similar. The overlap is quite large, and there's really a danger when you do the second projector that you get linearly dependent operators. Even you think, okay, you put the other eigenstate several electron volts away from the first one, but you might get the trouble, and GIPAW code might lead to bad values. I mean, in the beginning I had to gain the experience the hard way, so just trying, and I got very bad results, and that was because I had linear dependence between the 2 projectors. And the code now warns about that. So I show quickly, in the afternoon you will have the session using GIPAW, and what you first have to do, you have to calculate the ground state wave function. So you do the normal way, PWX, and in principle it goes all the same way as before, but already here you have to use the pseudopotential which include the reconstruction part. Then the input for GIPAW is actually very trivial. I mean, there's not much to tell. I don't know, there are just few variables which are available anyway, and usually most of them are technical, or the default values are good. So the job is just to choose. Here we calculate the chemical shielding. Here, electrical gradients. The prefix has to be the same as in the self-constant calculation, and the temp here, unfortunately, still we should actually change. It's the same as what you used for the where the temporary files are stored. And then for the chemical shielding, you have this Q value. So that's why I tortured you with many equations just to show that there's this Q, and that's the Q exactly like was derived. So this is what is used in that evaluation of the said, the code writes everything out that you can later, by post-processing, you can change the matrix of this shape of the contribution to it, or you can remove the contribution. Like basically the input is very, very small, or there are very few options. You run it same on the Pt2, and then I will quickly, we are in some of the overtime, and I will quickly introduce you the output. So the program GIPAW starts for the NMR calculation. The input of the output in the beginning is the same if it's electric field rate or NMR. So this was just run for processors, very interesting. But here you see the warning projectors are nearly even. This is benzene, and the N-type 1 is the carbon, and it says, well, this is actually, one has to look for what this is, but it's, the S projectors are almost independent. So, like for the oxygen, we thought that you have a gradient 2 operators which look completely different, but the overlap is actually very, very large. And it's difficult to get, I mean, really difficult, even though no matter which energy you put, difficult to get values that the overlap would be smaller than, let's say, 0.95. And if this gets too large, I think now the value is 0. If the deviation from 1 is less than 10 to the minus 5, the code stops, because you start to get, you have to invert a small matrix in the beginning, and inversion goes numerically wrong if the overlap is too large. That's why they shouldn't be linear dependent. The projectors, I mean, it's for the same species, the same L. But like I said, it's usually difficult to get smaller overlaps. So if you get really strange result, you might check in the beginning. It's really now the code should stop. The overlap is too large. And then quickly, for the two species, calculates contribution to the core. And for this pseudo, it's 200 ppm. Basically, in the case of hydrogen, there are no correlates. Then you can check some of the values from the outputs. There's a so-called F-sum rule, which is that should go to the. Can you help me? It's the number of minus number of electrons. If you have a full convergence of the calculation, so at least the cutoff is high enough, and if you have K-bonds, but these are molecules, so you are close to the 30, which is the value you should get. And then here one gets the susceptibility. There are two kinds of ways to define it. One has the velocity operator, Green's function, and the momentum operator, velocity, Green's function, velocity. Well, they are different here, but this is a molecular system, so the susceptibility actually doesn't make much sense. And then the real output, I mean, then first it tells you the layer shift, the diamagnetic shift, the paramagnetic shift. That's not so interesting. If you add them up, you add the macroscopic shape, you add the code contribution, you end up with this tensor. Then it tells you what is the average value or the isotopic value, and then it's, well, in this case the matrix is, or the tensors are symmetric, otherwise it would calculate the symmetric tensor, it would diagonalize it, tell the eigenvalues, because these are something that can be again compared to experiment, and then you calculate the asymmetric tensor, well, or the antisymmetric tensor. And in this case it's symmetric, so this is 0. But this is, so the isotropic one is the easiest one to compare with experiments. It's the fastest one, but sometimes one might be interested in this. And eigenvectors, they give you the orientation of the rotation of the coordinate system. So the electric field gradient, this is a kind of output that it gives. And actually, in this case, I didn't give any value for the Q. It's the default value. If you remember, the result is linearly dependent on the value for the Q. So you can later scale that, look in the tables what is the value for Q, and then one gets these two values. And this is independent of the Q, but this is proportional. So you get the full tensor, and then those two observable CQ and theta. And well, there was a trick. I mean, or there's some something wrong in this. I mean, there's no isotope for carbon for electric gradients. I just showed this for hydrogen still. Let's see. So to get this value, you have to give it the value for Q. And you rescale this value, and you would get something that you can compare to the experiment. Okay, just a quick acknowledgements. So Francisco Mauri is basically behind all this effort for GIPAW or NMR, DPR, and quantum espresso. Of course, Davide, who has done most of the implementation, I would say, is the hardest part. And then Thibaut Charpentier, who is an experimentalist, also doing calculations in France. And he has helped me a lot to understand what the NMR is about. So, do you have any questions at this point? We are 10 minutes late. Schedule, but if not, then shall we have a break, normal break, or 20 or 25 minutes?
Yeah.
25.
Yeah, 25. So we start 5 past 11.